So we're continuing our optimization and we're looking at example 3 here. So it says that FedEx states, and the little comment here above the arrow is directly from a FedEx website, little screen capture. So it states that a FedEx ground package can't exceed 165 inches in length and girth. Now that girth, just so you know, is the perimeter of a cross section. So kind of the definition of girth here is the perimeter in general, perimeter of a cross section. Okay, so that's what girth is. All right, now your company ships a large amount of these cylindrical packages, and you've been asked to find the dimensions of this cylindrical package that is going to have the largest volume. So let me actually specify here. You've been asked to find the dimensions of the circular cylindrical package. All right, so let's start by drawing a picture here. So we are going to have this circular cylinder here. So roughly something like this. And how is the dimensions when we think about a circle here? We're going to think a lot about its radius. And then, of course, we're going to have this length of this cylinder here. All right, so there's my little picture. And then we want to start by thinking about, well, what are we trying to optimize? And in this case, we're trying to come up with the biggest volume possible. So we are trying to maximize the volume. And again, kind of like example 1, let's just start with really the general formula for volume here, which would be just the area of the base times the height. You could think of it that way. I suppose that would be more if you were to put this on its end, sitting on the circular base here. So as we think about this in this perspective, you're really thinking about it more, I suppose, in terms of standing it upright here, right? So that's kind of the way you're thinking about that here. Okay, so the area of the base, we're just talking about the area of a circle. So we're really looking at just simply pi times the square of the radius. And then the height in this case is really what we're referring to as the length here. So we're going to call that L. So this is the volume that I'm trying to maximize. So just like example 2 and like a lot of the problems that you're going to have in this section, initially this primary equation is going to be in terms of one variable. So now we need to look at what is the constraining or the secondary information. I mean, if you want something with a really big volume, you could just make a really big cylindrical package, but we can't. We have a constraint here. And the constraint is that we can't exceed, just a second here, we can't exceed the combined 165 inches in the length and the perimeter of the cross section, so the length and girth here. All right, so let's go off to the side and write an equation that represents this secondary constraint information. So what we know is that the length plus the girth, which is the perimeter of a cross section. Well, a cross section here is going to be a circle, and the perimeter of the circle is really the circumference of a circle. So let's write this out first. Let's just say length plus girth has to equal the 165. So the girth in this case is the circumference of the circle. And so we have 2 pi r is our circumference. All right, so now we want to look and decide, does it make a difference? Is it easier to solve for L? Is it easier solved for R? And I think in this case, hopefully we can all kind of agree looking at this, that it's much easier in this case to just solve for L. If I solve for R, I'd end up having to divide by 2 pi and create unnecessary fractions. So our L is equal to 165 minus 2 pi r. So we are able to, I didn't mean to erase that, go off to the side here and set up our secondary or our constraining information. And now we have this solved for L. So we can go back into the original equation and we can take out the L, and in its place we can put this 165 minus 2 pi r. But of course everything else stays the same, so we still have the pi r squared. And now I could call this v as a function of r. All right, so now we have it in terms of one variable. That's great. Since this is just a monomial times a binomial, I would probably be pretty tempted, and I think I will just go ahead and distribute before I take the derivative. Your other option would be product rule. So distributing through the pi r squared, we're going to have 165 pi r squared minus 2 pi times pi, so there's going to be a pi squared there, and r squared times r is the r cubed. All right, so now we can just take the derivative term by term, just remembering pi is just a constant that's going to be carried along like any other. And so bringing down the 2, we're going to have 330 pi r to the first. And then bringing down the 3, we're going to have minus 6, the pi squared, and now r squared as well. All right, so to work on finding critical points, let's go ahead and factor out the GCF. So in this case, I think we can factor out a 6, a pi, and an r. Of course, the most important thing is at least getting the r factored out. And then just double check. Yeah. Okay, so 330 divided by 6, so that's my 55 here. So this is 55 in the first term, and then minus pi times r left in the second term. So that's a pretty good form of my derivative there. And so now I want to find where my derivative is equal to 0, or of course potentially where the derivative does not exist. But of course we don't have any issues of that here. So where the derivative is equal to 0, we do already have this factored, so that's good. So just going ahead with this and setting each factor equal to 0. So on my first equation, solving for r, I would divide by 6 pi. In my second equation here, I'd probably add the pi r over to the other side. So my first solution, my first critical point is 0. And then in my second equation here, I'm going to have pi times r is equal to 55. So dividing both sides by pi, looks like my second critical point here is this 55 over pi. And so if we wanted to think about that, 55 over pi, just so we have kind of a reasonable sense in our minds of what this is approximately 17.5. All right, so now obviously kind of like other ones here, we're going to throw out r equals 0, so we can't have a 0 radius, so no 0 radius length. It wouldn't make any sense. So most likely this radius of 55 over pi, or 17.5 inches, this is probably the right solution, but as of right now, all we really know is it's a place of horizontal tangency. So we need to verify. So we need to verify that r equals 55 over pi actually gives a max. And this time, so I'm using a variety of tests in this section. Let's use good old first derivative test. So in the first example, I did test for absolute extreme on a closed interval. The second example, we did second derivative test. Let's go ahead and just do first derivative test on this one. So this tends to be the favorite of students because maybe it's the one we did the most of. But this is just your sign analysis on your first derivative. So you're subbing into the first derivative, and then you're making conclusions about the increasing and decreasing behavior in the original. So you do want to put your critical points on here. 0 was a critical point, and then so is this 55 over pi, or approximately 17.5. Now, of course, it's not going to really make any sense to think about anything that's less than 0, so we can really just focus on between 0 and 55 over pi. So maybe we sub in just something like 1, so subbing 1 into your derivative. So if I look at the 6 pi r, that monomial would be positive, and then 55 minus pi is definitely going to be positive, so this is going to be positive, and so we're going to be increasing. And then if I sub in something bigger than this 17.5, so maybe we sub in 18, 19, 20, whatever you want to think about there, 6 pi r is still going to be positive, but now 55 minus pi times a really big number as r gets bigger is definitely going to make that binomial negative. Positive times negative is negative, so we are going to be decreasing. And so, of course, if we're changing from increasing to decreasing, that does tell us that at x equals 55 over pi, that this is going to be the location of a max. All right, so we have verified that with the first derivative test. Now let's go back up and see exactly what questions we're supposed to answer. And in this case, it's the dimensions. So that means the radius and the length. Sometimes they may ask you for what's the actual max volume, in which case you would just sub this back into the volume function. So we already know one of the dimensions. So we already know that your radius is the 55 over pi inches. And then subbing back into the constraints. So the one that you subbed back in for the L, so that was the 165 minus 2 pi r. So 165 minus 2 pi, and then replacing r with our 55 over pi. And so the pi's there are going to reduce, and so we are going to have, so 110, so the 165 minus 110 should put us at 55. So our length in this case then, so the length is 55 inches. So these would be the dimensions of a circular cylinder that would still fall under this constraint to not be declared as like U.S. domestic freight or something. So this would be the dimensions that would give you the biggest volume possible without exceeding those restrictions by FedEx. So maybe we'll do one more example next time.